The other day, we studied about how the PCl5 can be used for making alkyl halides from alcohols. So if you add PCl5 to alcohols, you will get alkyl halide here, and the other product will be POCl3 and HCl. Okay, so this is what we have seen it once. Yeah. Now, if you add PCl5 on any double bond, you'll get two chlorides. Same way here also you'll get two chlorides. Whether it is in cyclic form also, we'll get this as two chlorides here. Okay. So you can see the mechanism goes something of this sort where the oxygen will attack here on the empty orbital, C will come out, and then the C will attack from here, double bond will form, and one more time the Cl will attack. Okay. So that way you will notice that there are two chlorides which are coming across. Next, if you see the reaction on ethers, right, ROR, first the lone pair will connect, one of the chloride will go, and then the chloride will connect, attack on one of the R, which is uh, less substituted, or which is relatively better for SN2 reaction. So between R and R dash, you have to choose which one is better for SN2. So based on that, Cl minus will attack, and then the bond will break here. Again, I'll get R dash O PCl and Cl, for which it will make a double bond here. Cl minus will go, and the Cl minus will attack simultaneously from here. So that will make it as four-member cyclic transition state, and eventually you'll get this as R dash Cl. Okay. So both of them, one will be RCl and the other one will be R dash Cl. If you notice the examples, we'll get this as POCl3 and 2 moles of this, or 1 mole of this and 1 mole of this. Yes, beta. Someone has a doubt? Anurag? Right. Check. This side, if you notice, this side it will go for SN1. This part it will go for SNI. See, SNI means what? SNI is the case where there is a simultaneous movement of double bond, I mean breaking of bond here, and from the same side chlorine is attacking. So when it happens from the same side, we will get this kind of transition state, and finally you will get the product as R dash Cl. Okay. Right. Next, you see here also there is an ether. This will break. While you are breaking on this end, you will notice that because you are breaking on this side of the part, definitely SN2 will make an inversion here. So this part will undergo inversion, while this part will remain the same. Okay, because it is retention part. Since it is going for SNI, it will undergo retention. Clear, everybody? So you need to figure out which one is SN2 based, and that you have to convert into as inversion, and rest of that you have to keep it as a retention. Next, see the reaction with epoxides. See, we know that when you have an alkene and we add MCPBA or any peroxy acid, we will get an epoxide first. Now, this epoxide, when you treat with PCl5, will also give you dichlorides here. Just like aldehydes are ketones, here also we can get dichlorides. But this time the chlorides will be on two different carbons, which we call it as vicinal dihalides. We get this as vicinal dihalides. Check the mechanism. So the lone pair from here will attack on phosphorus, right? Removing one chlorine out. So we will get this particular compound on which Cl minus will attack, removes this bond here. So we'll get one chlorine attached here. Again, we have OPCl4, same logic here. This bond, you can break it onto the double bond here. This will become a double bond. This Cl will connect from this end. So Cl minus will attack here. So we will get this Cl and Cl. We'll get this as POCl3. Got it? So I hope all of you understood that. This is how we'll get this as vicinal dihalides. Vicinal dihalides. Okay. See here, O and O is connected. So once you get this, Cl minus will connect. So we'll get this chloride. And the other side will be retention. So the next chloride will be always retention part of it. So this chloride will be inside, this chlorine will be outside. Okay. Here also the same logic, chlorine inside and chlorine outside. If you notice epoxide, if you take cis form and epoxidation is a syn addition. This is a syn addition. So when you have a syn being added on cis, we will get this as trio. That means both will be on the same side. Both will be on the both will be on the same side, which is erythro. And now when you use PCl5, one side we are getting Cl, the other side we are adding Cl from the opposite side. So therefore it is like an anti-addition. So we'll get two chlorides on the other side here, like this. So what we are getting is pair of enantiomers. While if you have a transform, when you do MCPBA, which is again a syn addition, and you know that trans plus anti-addition is this trans plus syn addition. Trans plus syn addition, right? Will give you trio. So now we will have a trio form here. You can see this methyl and this methyl are inside and outside. So that's a trio form on which when you add PCl5, it is like trans on trans. So that makes it as erythro here now. So it is an erythro kind of a form, which is a meso form because of the plane of symmetry that exists here. Correct? So if you come across PCl5 on epoxides, just ensure that you'll make something like an anti-addition. Next, see the reaction of SOCl2. SOCl2, which is thionyl chloride. Okay. Thionyl chloride with alcohol. See, ROH alcohol plus SOCl2. If you treat with this, the new type of reaction, which is SNI, will happen to get RCl, SO2, and HCl. Okay. So basically, this oxygen will go away with sulfur, and one chlorine will collect here, and one chlorine will go away with hydrogen. That's how we'll get HCl, SO2, and RCl. Now, best method to prepare primary alkyl halide from alcohols, as SO2 and HCl both will be separated away very easily due to its vaporization. You can notice that in earlier case, when we use PCl5, it was difficult to remove the other compounds from alkyl halide. But here, SO2 and HCl easily evaporates, keeping the alkyl halide as the remaining part. Now here the mechanism happens something as an A and E type. A and E means first addition, then elimination. Okay. Earlier PCl5 was also like substitution first directly, removing chlorine, right? But here, rather than removing chlorine, it is like first an addition, then an elimination will happen. See, oxygen will attack on sulfur, pi bond will get delocalized towards oxygen. That means it has undergone addition, right? A nucleophilic addition has happened. Then this O minus will try to close it back because S double bond O is a very stable bond. Cl minus will come out. As the Cl minus is coming out, that will take away this H plus and vaporizes as HCl. It will come out as HCl vapors. Clear, everyone? So now what we left out is ROS double bond O Cl, right? ROS double bond O Cl is what we left out with. Now this compound, if you notice, it will make an internal change here. So here the bond breaking will happen. On the same orbital, Cl will also start connecting. So bond breaking as well as bond making happen simultaneously via four-membered transition state. That gives you RCl now and SO2. SO2 will also come out as vapors. Clear? So if you notice that HCl has also come out as vapors here and SO2 has also come out as vapors here. Correct? This is an SNI reaction. Why I am saying I is like an internal attack from the same side. If the attack is from the same side, right? So that is going to be SNI attack. Now, if the reaction is given this way, right, where SOCl2 is present in the presence of an nitrogenous base, okay, something like R3N, tertiary amines, or pyridine, clear, like this, pyridine, or any of the nitrogen based bases. If that is the substance you are taking as a solvent, see here in this case, I'm taking ethers as the solvent. Here I'm taking ether as the solvent. But instead of taking ether, now if I take pyridine as a solvent, now the reaction will happen via SN2 instead of SNI. Reaction is the same. You'll get this as RCl, SO2, but instead of HCl, now you'll get a salt. Why? Because HCl is an acid. That acid will react with this nitrogenous base and converts into a salt form. Okay? Let me show you how the steps work. First, alcohol, lone pair of alcohol will attack on sulfur. We will get this form, right? Then this will make a double bond. This Cl will take away this H plus. You will get this form, right? Up to this, the steps are exactly same how we did it for the earlier case, SNI. But from here, you notice in the presence of pyridine, HCl will not be evolved out of the reaction. It will undergo an acid-base reaction and it will generate a free chloride ion because it is a salt. So salt will be soluble, giving away Cl minus ions in the solution. So instead of internal attack now, the Cl minus will attack from the external source because as a minus charge, as a negative charge, that will have more nucleophilic nature to attack on alkyl group. So it will attack, this bond will break to make it as a double bond and Cl minus will come out. So you will get this as RCl, SO2 and Cl minus. But this time it is via SN2 mechanism. So very critical. SOCl2 without nitrogenous base is an SNI mechanism. With nitrogenous base is a SN2 mechanism. Got it? So keep this difference. Okay. Now notice ROH when you attack with sorry, here it is. See the steps here. Pyridine is taking away this H plus here, right? Cl minus will come out here. So that makes it pyridinium chloride. And Cl minus from the opposite direction is attacking. This bond will become SO2 and Cl minus. This reaction is called as Darzin's halogen reaction. This is called Darzin's reaction or Darzin halogens reaction. Okay. So Darzin's reaction is via SN2 mechanism. Regular SOCl2 is an SNI mechanism. That is internal attack. Okay. Everybody clear with this point? See the questions here. For example, if there is a chiral center given, okay, if there is a chiral center given, if it is SOCl2, if it is only SOCl2 in ether, then you will take it as SNI. So SNI means the product will be inverted. So we'll have this as CH3 here, D here, and H here, plus SO2 plus HCl. That should be the product. So you can notice the configuration here. Here it is 1, 2, 3. Priority wise, it is going clockwise, which means it is R configured. So originally it was R configured. Now it will be, sorry, my mistake. I wrote it wrong here. Retention. So I need to write it in retention form. So it is retention. So I have to write it as CH3, Cl, D, and H plus HCl plus SO2. Okay. So here you can see 1, 2, and 3. So this is an R configured. So that would retain here. So this will also remain R configuration. While if you notice with pyridine, it will be D, Cl, CH3, and H plus SO2 plus pyridinium chloride. So instead of coming out as HCl vapors, now it will be pyridinium chloride available. And the configuration here will be S configuration. Okay. So remember that with pyridine is only called as Darson's reaction. Okay. Same logic here also. If it is SOCl2, it will be SNI mechanism. SNI means retention. So I'll write this as the product. So rest will be SO2 and HCl. Same question. If you write it in terms of pyridine, then this is how I'll write the chloride. So SO2 plus PHNH plus and Cl minus. That is about writing the pyridinium chloride. Notice here also, if nothing is given, you will always take it as SOCl2 in ether. So in the case of ether, what do we have? OHCl will be here, methyl will be here, H, D and methyl. While here, you'll notice that Cl will be here, H, methyl, H, D and methyl. So this will be SO2, SO2 and HCl. Here it is pyridinium chloride. Right. Next. You see SOCl2 in SN2 dash. See, if there is by chance a double bond present here, listen to this everybody carefully. If there is at an allylic position, if there is an allylic position, first step is the same. First oxygen will attack sulfur, first we will have this formation here. So that is S double bond, then we have like this O, S, O minus double bond O, sorry, Cl and Cl. Up to this point, it is okay. Okay. With H and plus here. Correct. Now, Cl minus, as soon as this closes, instead of Cl minus attacking here, now the Cl minus will start attacking at this position. Okay. You can see the cyclic structure 1, 2, 3, 4, 5, 6. A 6-membered cyclic structure will form and Cl minus will attack on this end. Okay. So this is how the attack would take place, where you will have closing of this bond and Cl minus will attack on this bond. Clear? So you will see the product here now. So I have written it. I'll just remove this out. Yep. You can see this now. Yeah. So 6-membered ring will form here. So you can see the attack would happen from this Cl end. This bond will move again. So we will get a double bond on the terminal carbon. Okay. So guys, listen, when instead of attacking on one particular direction, like instead of attacking on the same carbon from where the leaving is group is going, if the attack is on the other carbon, then you will call it as a hash here, dash. So this will become SN2 dash. So this is an SN2 dash reaction. Clear everyone? This is SN2 dash reaction. So that would make this as a product. Okay. So this type of allylic substitution is called as SN2 dash mechanism. Okay. This week you also have allylic substitution. This would be a question. Okay. Be careful with it. Everyone understood that? Right. So the same logic here. Here we have this as the alpha position, beta position, gamma position. Okay. So where does the attack would be? At the gamma position, so that this can move here and this oxygen can leave from here. So you can see the mechanism, how it happens, right? So from here, Cl will attack on the gamma position, double bond will move, oxygen will move here, and by 6-member transition state, this is the product. And now listen up, because this is at a double bond position, okay? Because this is at a double bond position, the attack of chloride could be from the bottom side of the plane or from the upside of the plane. Up or downside of the plane, either ways, you will have, attack being seen, which means this will become a chiral center with a racemic mixture as a product, because attack would be 50-50% observed. So the product you will get is 50-50%. Okay. Done. Same logic here also, you can see SOCl2 is there. So Cl will attack on this gamma position. the double bond, sorry, here, gamma position, double bond will shift here, O will go here. So therefore, chlorine will come at this position. So I hope all of you understood how the allylic substitution is working. Right. Now, just as a tip, just like how we have done it for alcohol, the same logic you can apply it for ethers, for acids, for esters, and so on. You can see SOCl2, if you write it with alcohols, this R and Cl will go away, this H and Cl will go away, and this oxygen and sulfur will make SO2. And that line is also helping us to understand the same thing. This R and Cl will go away, this oxygen and SO will go away, and this R and Cl will go away. Okay. So here ROCl will form, acid chloride will form, and here R double bond of Cl, and here also R double bond of Cl. So two types of acid chloride will form. In esters, RCl will form, and one more RCOCl will form. Okay. So whenever you see about acids or esters or anhydrides or ethers or alcohols, they all will react with SOCl2 to give these respective products. Okay. This is one of the very commonly asked mains question. So please learn it. In any of the cases, what is the product that you have to write? Mechanism based question where you have to understand the chirality, whether it is retention, inversion. That is something we need to learn properly for advance. But mains is concerned, this is the thing which you need to know. Okay. In case of amides also, same logic, as just like PCl5, here also it will go for dehydration. This H and O will come out two times. So therefore, we'll get this as RC triple bond N. Okay. Reaction with ethers, same logic. O will attack here first. We will get this. So double bond will close. Cl minus will come. Okay. So once the Cl minus will go away, from there the Cl minus will attack, and this would form here. And here you'll have an internal attack. Okay. Similar to that of PCl5. Everything is exactly same like PCl5 here. Okay. First SN2 attack, next an SNI attack. Okay. Done with it. This is for ethers. So, like I said, you can see this is R configured. If you take CH3O minus, right? If you have this, we have Cl, F, and CH3. Now, see the point here. Lot of cases use the word inversion. Okay, we always use the word inversion, right? Considering that the configuration is changed, right? But even after the backward attack, even after the reverse attack, it might happen that the configuration is not changed. For instance, if you have fluorine, chlorine, hydrogen, and CH3 are present, you will notice that 1, 2, 3, this is how the rotation is happening, which means this is R configuration. This is an R configuration. Now, if you attack CH3O minus, which will go for an SN2 attack. If it is an SN2 attack, it should come from the backside, remove Cl. So where are we getting fluorine now? Fluorine is coming at this position. OMe is here, CH3 is here, and H is here. Now, because Cl was replaced by oxygen-based compound, priority now will be more for fluorine. So fluorine will get priority 1. This is priority 2, priority 3. So again, when you rotate, it is becoming clockwise. Okay, so understand that whenever there is an reverse attack, does that mean every time Walden inversion has to happen? Not necessary. That's an important statement. Remember, not always. Okay, backside attack, backside attack of nucleophile may or may not lead to inversion. May or may not lead to inversion. Okay. So it is not necessarily it has to undergo inversion. It may or may not lead to inversion. Okay. In most cases, it does. As a generic statement, when we say it will go for Valden's inversion, we say it is yes, but it is not compulsory. Okay. If it is said it must change to inversion, that is incorrect statement. Okay. I think this case is clear, everybody. Yeah. Check out next case now. What about reaction with PX3? Okay. Now, alcohol, when you treat with PCl3, it will become 3 moles of RCl and H3PO3. Okay. So basically, first mole will attack on the empty orbital, Cl minus will come out. This is the product you will have. So Cl minus will take away, usually what we think, this Cl minus will take away this H plus, correct? You will get this as ROPCl and HCl. Okay. And HCl being a strong acid here, the lone pair of this oxygen will again attack on H plus to bring this back here. Correct. So typically what would happen here is the lone pair present on oxygen will attack, sorry, the Cl minus present on this would attack on R, breaks this bond, and you'll get this as POH, Cl and Cl. So what are we getting? That it is 1 mole of RCl and POH, Cl and Cl will be present here. Okay. So now what we can say here is the second mole will have the same logic here. ROH, the second mole now. One side we have OH, other two chlorates are still present. So the lone pair of oxygen will again attack on phosphorus. You will get the same thing. Cl minus will again attack on R. You will get two OH groups and one more mole of RCl. If you attack similar way, ROH for the third time, Cl minus will attack on the third mole. You will get this as RCl. Okay. You will get this as the phosphorus acid. This phosphorus acid, basically we have phosphorus with three OH groups, undergoes tautomerism. That means this lone pair will become double bond here, right? And phosphorus will get negative charge, which will take H plus from here. And that's how it will become a phosphorus acid. This is the final structure which you need to show. Okay. The structure will be unstable in this form. Final structure will be more stable in this form. Okay. So you can see 3 moles of this, if you notice, when you add with PCl3, inversion will happen in all 3 moles of it. So Cl will be on this side, methyl will be on this side. You can see the product, and H3PO3 is formed. Okay. So now when you react with PCl3, again the same logic. OH will be in outside. Here OH is inside. Here PCl3, OH is outside. Now the Cl is inside because it is SN2 mechanism. Here is OH is upwards. Here Cl is downwards because of SN2 mechanism. Overall reaction is this, something which you need to learn, that 3 moles will give you all of that. Okay. So to put in all the reactions together, this is one such reaction which we need to remember. And here it is 1 mole POH ROH plus PCl5. When you treat with PCl5, it will use only 1 mole RCl plus POCl3 plus HCl. This is a product. When you take ROH plus SOCl2 in ether, this is also in ether, this is also in ether. So ethers are the most favorable solvents in this case. So we will get this as RCl plus SO2 plus HCl. Okay. So these are the 3 important reactions for preparation of alkyl halide from alcohol. Everybody clear on this point? Okay. Next, check out PBr3. PBr3 will also undergo SN2 mechanism. You'll get 3 moles of this Br. OH is here. After the inversion, Br will come here. OH is coming out of the plane. Br will be inside the plane, right? PI3, when it comes to PI3 is prepared in situ. In situ means just at the point of reaction. Before that means in the presence, in the situation. In that situation only we'll prepare it. That is, red phosphorus plus I2 will become Pi3. This Pi3 will again decompose back to red phosphorus and I2. So that's why to prepare Pi3, we should only prepare at the time of the reaction. So you can simply write it as P plus I2, or you can write it as Pi3 also. So 3 moles of this alcohol, when you treat with Pi3, we will get this as 3 moles of alkyl iodide and H3PO3. And you can see OH is on the right hand side. Now iodide will be on the left hand side after SN2 reaction. Clear everybody? So these are main SN2 type of reactions in alkyl halide. Okay. Only these three important reagents: PCl5, PCl3, SOCl2. Okay. Now let us do the comparison towards the SN2. Like which one is better? What is the rate of these reactions? Okay. Check out. First, CH3Cl versus CH3CH2Br. I told you that bromine is a better leaving group, right? So it is based on the leaving group ability. So leaving group wise, Br is better than Cl. So the rate would be more for that. So this will have more rate compared to that of Cl. Second, when it comes to crowding, this is primary position, this is secondary position. So primary is always more preferable than secondary. So this is how it will vary. So rate rate of SN2, rate of SN2, let me remind you, methyl halide is greater than 1 degree, greater than 2 degree, greater than 3 degree. Next, here, if you notice between these two, this is an allyl position. This is also allyl, but here the ring is restricted, because of which if you try to start removing it, there will be a partial positive charge that will bring anti-aromatic nature. So what will be the reaction now? So that's why this will be the case here. Okay. So you can see this is allyl. Okay. This is also allyl with resonance here. So if you notice, allyl of this form, they will have resonance more here. So that will be less supportive to that of chloride. So this would have more support of pi bond towards chloride. So we can say that neighboring support, neighboring pi bond support, neighboring pi bond support in transition state. So that will increase the stability in transition state. Next, lone pair carrying without lone pair. Obviously, lone pair will be strongly helping it in SN2 mechanism. So therefore, that will be more. So lone pair carrying on alpha position will stabilize transition state. Will stabilize transition state. Similarly, here also lone pair carrying without lone pair. So definitely lone pair would be better. Next one, this is allyl. This is vinyl. Vinyl will not make any reaction, and then 2. So which one is better? So allyl is better than 2 degree, then no reaction on vinyl. Next one, primary, methyl primary, secondary. So reaction will be better for methyl than primary, secondary. Now come to H here. In case of H, Cl is on the axial direction. Here Cl is on the equatorial direction. Okay. Now notice this one. When a nucleophile approaches, see here, a nucleophile is trying to approach. It can approach from the backside here, because sigma star will be here. This is where the sigma star will be. And if it has to approach here, it has to approach from this end. In this case, correct? But what would happen in this case here is we will have hydrogen and hydrogen here. So this entire environment will have 3 hydrogen groups present here. Remember, what do we used to call this? Okay. Diaxial repulsions. Remember, 1,3 diaxial repulsions or 1,5 diaxial repulsions. So because there are hydrogens present here, because of the diaxial repulsions, this side nucleophile approaching and attacking will be difficult. But here on the axial direction, it is more easier to, attack on this. And moreover, chlorides on equatorial are more stable compared to chlorides on axial. Why? In axial direction, they will always have repulsions with hydrogen, right? So thereby, I mean, repulsions in the sense here, this will have delta negative charge here, and this will also have charge on hydrogen here. So they will always have a repulsion. So van der Waal repulsion, it is not some hydrogen bonding or something. It is because of the van der Waal repulsion. So this becomes easier to break. Axial becomes easier to break. Remember, due to 1,5 or 1,3 diaxial repulsions. Diaxial repulsions. Okay. Axial will be more reactive than equatorial. Axial will be more reactive than equatorial. Next. Check out 1, 2, 3 here. Okay. This is completely vinyl. This is allyl. This is allyl. Within allyl, iodine is better leaving group. So again, so therefore iodine will be better than fluorine than allyl. Okay. Next. Here, this is at bridge position. This is at normal position. Bridge position, no reaction. Okay. No SN2 on bridged position. Next. Check out K. This is at 3-membered ring. This is at 6-membered ring. I told you that in 3-membered ring, reaction will not happen. Okay. Why? See, for 3-membered ring, the sigma star is here. So approaching that sigma star will be very difficult for nucleophile because of the blockage. But when you have 6-membered ring is not planar. It is actually a chair-like shape here. So you can see Br will be here. So sigma star is very easily accessible. Got it? So reaction is better for 6-membered ring, then 5-membered ring, then 4, then 3-membered. Okay. Here, next. Between these two. Between these two, if you notice, this is benzyl, this is phenyl. So benzyl is better than that of phenyl. Okay. Due to, again, support on the transition state. Benzyl will stabilize transition state of benzyl will stabilize the transition state of SN2 mechanism. Right. Done, everybody? So I hope all of you got an idea about SN2 reactions. Now let's follow through SN1 reactions. SN1 is a unimolecular nucleophilic substitution reaction. Okay. So that is, if you notice this one, we have Br, it is at a tertiary position. And if I use aqueous OH minus or simply water for that matter, even if you use only water also, slowly it will start departing into Br minus and a carbocation. Okay. And on that carbocation, OH will attack and you will get this plus and minus. That is racemic mixture you can get. Step one is what, first, when you have this alkyl halide taken in water or any polar protic solvent, when we take it in polar protic solvent, they will start having an attraction with carbon and halogen because of their electronegative differences. They will always have partial positive and partial negative charge, and they will start making bonds with water, van der Waal interaction with water, because of which this bond will start becoming weaker. Okay, so due to this dipole-dipole interaction between water and the halogens, you will notice that the bond will start becoming weaker and it will break into carbocation and Br minus. Now, carbocation is an sp2 environment, sp2 hybridization. So these three are on one plane, and this is all coming out of the board here. and then one lobe is here and the other lobe is on the back side. Now the OH can attack on either side. It can attack from this end or it can attack from this end. So the chance of OH attacking can give you two products. One OH from this end, the other OH from this end, which converts into a racemic mixture. So we will get into a racemic mixture form. If you notice the energy profile, starting from this reactant onwards, we raised towards transition state 1. From there, we came to carbocation formation. From the carbocation, again a small bit of transition state towards the product has been formed. So you will notice there will be at least one intermediate forming in the case of SN1 reaction. A minimum number of steps are 2. Number of steps, if you notice, they are at least 2. Number of transition states are also at least 2. Number of intermediates are at least 1. The first step is the rate determining step, which is equal to K into Rx. Order of the reaction here is 1. Order of the reaction is 1. It is independent of concentration and nature of nucleophile. That is, generally, no, nothing. Okay, when it comes to order of the reaction, you will see that it has order number 1 and it will be independent of nucleophilic concentration. So typically weak nucleophile is preferable here. So here it is, weak nucleophile preferable. Next, it exhibits secondary isotopic effect. Okay, I'll explain you what is secondary isotopic effect. Okay, but just remember that both SN1 and SN2 exhibit secondary isotopic effect. Okay. Why is that so? See, if you compare reactivity between this tertiary chloride and this tertiary chloride, here we have carbon with 3 methyl groups and then chlorine. Here we have carbon with 3 methyl groups, then chlorine. But here this methyl is of CH3. Here it is CH3. So CH2 with H here and CH3 here. While here also, if you notice, this would be CD3, CD3 here, CD3 here, and CD2 and D here. Okay. Now, once it becomes a carbocation, so this Cl will be removed. You'll get carbocation here, here, and here. Now, this carbocation is stabilized by hyperconjugation. But for hyperconjugation, here we have to break hydrogen. Here we have to break deuterium. And you know that bond dissociation energy wise, C and H bond, epsilon of C and H bond is weaker compared to that of C and D bond. C and D bond is stronger, which means hyperconjugation is less in the case of second one. So if this is 1 and 2, so I can say stability wise, if you notice, one will undergo better hyperconjugation stability and second will have less hyperconjugation stability. Okay. That's why you will notice that if hydrogens are replaced by deuterium, the rate will always decrease because it will be less stable. Clear everyone? Check out the graph now. Rate versus the concentration of the reactant, substrate Rx. It will vary linearly because we just learned that rate is equal to some constant into substrate concentration power 1. And if we have nucleophile power is 0 here. So it is independent of nucleophilic concentration. That's why nucleophile, no matter how much you increase, the rate will remain same. Okay. This is about SN1 reactions, guys. Check out stereochemistry of SN1. If SN1 attacked by nucleophile and carbocation gives equal percentage of dextro and levo, then we call it as racemization. Isn't it? Racemization is a concept of 50-50% of dextro and levo. But usually what happens, the racemization is observed to be, some degree of inversion. That means whatever racemization we are seeing, It is not 100% racemized. That means some part of extra inversion is present. So I can say out of 100 percentage, 95% may undergo racemization, but 5% remains more inversion. Okay. So therefore, the percentage of inverted product is more than the retention product. This can be explained by this following nucleophilic attack in a concept called tight ion pair. So remember this concept. It is called tight ion pair. Think this way. When you take RBr into the solvent, as soon as you put it to solvent, they'll slowly start getting charges. And you'll get R plus and Br minus charges. Okay. And there is not much of a distance that has lost, but only the charges have been created. So this situation is called intimate ion pair. That means they are very close to each other. R and Br are very close to each other. They are like an intimate ion pair. Now, in the equilibrium, slowly they'll start departing. So R plus will be separated, Br minus will be slowly separated. But yet the distance between them is not so far that there could be other molecule that can come and attack R plus. So this is called solvent separated ion pair. This is called solvent separated ion pair. Third one is completely free ions. Now, this is completely surrounded by solvent. This is completely surrounded by solvent. These are three stages which would happen before it converts into an SN1 type of reaction. Now, notice this. Intimate ion pair or a tight ion pair are the first stage due to the solvent dipole-dipole interaction. But carbon attains enough positive charge to attract a nucleophile. Therefore, nucleophile or the solvent will start attacking R plus, but only from the backside. So you can see that in this case, here also as well as here also, in both cases, the nucleophile will start attacking R plus from the backside, because from this side, Br won't allow, because Br is already there. Here also Br won't allow. But from the backside, we can still attack the solvent, right? Solvent is a nucleophile like water. Water is a nucleophile. Okay. So that's why you will see solvent will start attacking R plus from the backside already. Okay. So R plus is shielded by Br minus from the front side. So solvent separated ion pair is second stage where solvent has separated the ions, but still the attraction of R plus and Br minus is felt. Next, nevertheless, attack of nucleophile can happen from either side, leading to the racemization. Okay, which means from this stage onwards, right? More of this will be there, but slowly the attack from the other side will also start. And when attack from both sides will start, that will and if the composition, I mean, if the rate is same, then we say the racemization is happening. Okay, so that was we are trying to explain here. So solvent. That is solvent separated ion pair. In that case, we can say mostly racemization is favorable. Free ions or solvated ions is the last stage where ions are completely independent. So they will only lead to racemization. Then, so you can notice that more stable the carbocation, greater is the percentage of racemization. And more nucleophilic the solvent, greater is the percentage of inversion. Students, very important line. Understand that carefully. So if this carbocation is stable, percentage of racemization will increase. Okay, because it will racemize faster. It will not hold as a tight ion pair for a longer time. Or if the nucleophile strength is also good, if they are stronger strength, then also you will see the percentage inversion will be more. Next, solvolysis.
Sir,
Yes, beta.
sir, once can explain second step.
This one, solvent separated ion.
Yes, sir.
Okay, listen. In the case of solvent separated ion, beta, the distance is far away from R and Br. Okay, but they are still attracting with each other. There is still an attraction between each other. Clear? So now read it out. When solvent has separated the ions, but still attraction of this is felt. Nevertheless, attack of nucleophile can happen from either side, which means in this case, water can slowly start attacking from this end also, and from the backside. Anyway, it is continued because backside here it was happening, here it was not happening. So backside is still continued. Now slowly the front side also has begun. And by the time it reaches to the free ions, completely 50-50% is observed. Clear, beta? Satvi, I hope you understood.
Yes, sir. Yes.
Now you could notice that more nucleophilic nature of the solvent, greater is the percentage inversion. Now, notice this. Substitution reactions where the solvent itself act like a nucleophile, that is called as solvolysis. And SN1, SN2 both can show solvolysis depending upon the reaction. So you can see, for example, if you have this tertiary alkyl halide added to water, so slowly in no time you will see that chlorine will get departed, and the solvent which is present, if it is water, then water would attack here, converts into an alcohol form. Okay. See the mechanism here. Chlorine is being removed, carbocation is formed. Water will attack quite fast here. So we'll get this OH2, removing H plus, you will get this as OH. Okay. If you check out the energy profile, see what is it? The number of arrows you have, right? 1, 2, 3. The number of arrows you write, that implies that you have to write 3 transition states. Okay, because between every arrow there is one transition state. Here there is one transition state 1. Between these two there is transition state 2. Between these two there is a transition state 3. Correct? And every time you are going towards more stable carbocation. So first is this carbocation, next is this carbocation. But here the stability is not based on rearrangement here because of the extra bond formation. This positive charge will get an OH2, which is an extra bond. Extra bond will always lead to stability. So therefore this will have lesser energy, and from there finally you get the alcohol product. So I hope everybody understood energy profile. Clear? So check out, total number of steps are 3, transition states are 3, intermediates are 2. So there are 2 intermediates forming. Next, alcoholysis. Alcoholysis means when you are adding alcohol. If you add water, it is called hydrolysis. If you add alcohol, it is called alcoholysis. If you add ammonia, ammonolysis. If you're adding benzoic acid, okay, benzenolysis, like that. If you notice ammonia being added here, this is going to happen via SN2 because it is at least crowded carbon. So simultaneous attack, simultaneous removal. So first you will get this one. If you have excess of CH3Cl, again nitrogen will attack, you will get secondary. If you have still excess, again nitrogen will attack, you will get tertiary. Again, if you have excess, again it will attack, it will get quaternary. So if alkyl halide is excess, you will get up to quaternary salts. If only ammonia is in excess, right? This one is in limited amount, then it will be major. Check that out, everybody. I hope all of you understood that. Right. So hydrolysis, alcoholysis, and ammonolysis. Okay. Now, see what are the factors that are influencing SN1. First one is the formation of carbocation. Okay. So I can say that rate of SN1 is directly proportional to stability of carbocation. So you can see this is, methyl 1 degree, 2 degree, and 3 degree. And definitely 3 degree carbocation will be more stable than all others. So this is more stable. Next, here there are 3 methyls. Here there are 2 methyls, 1 phenyl, 2 phenyls, 1 methyl, and 3 phenyls. So 3 phenyls carbocation is highly stable. So that is how carbocation stability will be. And rate of SN1, if you notice. So, if you compare A, B, C here, what will be the rate of SN1, everybody? You just need to check out stable carbocation. B is a stable carbocation, allyl. A does not have any carbocation. C is an anti-aromatic carbocation. You can see if you remove this, you will get positive charge. It is anti-aromatic carbocation. So rate of SN1 will be B, A, and C. Clear? Check out the second one. Done. So if you notice the second one, you'll find this between these two. OCH3. OCH3 is a donating group. So this is a donating group. It is donating by plus M and it is withdrawing by minus I. But the overall it is donating effect. NO2 is overall withdrawing effect. It is withdrawing by minus M. It is withdrawing by minus I. Overall also it is, electron withdrawing group or deactivating group. So obviously carbocation is more stabilized with activating groups. So OCH3 will stabilize this. Nothing is there, still is okay compared to that of withdrawing group here. Okay. So A is greater than B is greater than C. Between A and B, you will notice that A is better because this is benzyl carbocation. This is benzyl carbocation. And while this is vinyl carbocation. Between benzyl and vinyl, A is greater than B. Next. If you notice Cl here and Cl here, just now we have learned that due to diaxial repulsions, this chlorine bond will be broken more easily. So remember that C and Cl bond of axial will require less energy compared to that of C and Cl bond of equatorial. This is bond dissociation energy. Because of which I can say which one is more reactive here. So if you notice B is more reactive than A. Okay. Axial is better than equatorial. Fifth one. ABC. If you notice this here, we can say that second one is allyl, first one is 2 degree, third one is vinyl. Vinyl will not make any SN1 or SN2 reaction. So B is greater than A, then E. Okay, this is C, sorry. We see. Next one, between these two, there are two methyls, one phenyl. Here there are two phenyls, one methyl. So what will be the race here? B is greater than A. Similarly, here there is an allyl, but here there is a resonance support of carbocation, which is huge. So C is greater than that of A is greater than that of B. Next one, once you get a carbocation, right? So it is like carbocations are forming like this. We have nitrogen here. Okay, carbocation is forming here. So the other form is we have oxygen here. Carbocation is forming here. So you will see that carbocation is more stable when you push it here. So this is more stable compared to the of O. So therefore, what will be the rate here now? Right. So what is the order here now? Suppose if at all I take this as A and B here. So you can see that nitrogen is a better donor than oxygen. So A will be greater than B. Next, if you have A, B, C, D here, now if you want to check out the rate, you can see you just count the number of alpha hydrogens. Alpha hydrogens here are 3, alpha hydrogens here are 2, alpha hydrogens here are 1, and alpha hydrogens here are 0. So more the alpha hydrogens, more is the stability of carbocation. So A better than B, better than C, better than D. Next, between benzyl and lone pair supporting group. So lone pair will have much more support. So B is greater than that of A. I gave you the carbocation order the other day. So I hope all of you remember that. So A, B, C. A is at tertiary, this is at primary, this is at secondary. So tertiary is always better. So A is greater than C, greater than B. Okay. Next. Here, this is phenyl. This is allyl. This is benzyl. First one is benzyl. I'll write down here. Benzyl. This is simple allyl. This is 1 degree. So obviously 1 degree will have the least. and benzyl will have the most. So A greater than B greater than C. Done. Check out on 13th one. 13th one, this is also bridged, and this is non-bridged. So they here carbocation stability is very good because it is tertiary. Now between these three, that bridge which will have more strain. You can see this has less carbons, it has more strain. More strain carbon will be difficult to get carbocation. They'll have different difference in making a carbocation, right? Why? Because it will have more strain. This is 5-membered ring, it will have more strain. While this has 6-membered ring, it has less strain. So we can say that C is better than A is better than B. And everybody, next. Elemental effect. We will notice elemental effect, right? When bond dissociation energy is weaker. That is, Ri has weaker bond compared to RBr, RCl, and RF. So the rate would vary this way. Okay. So it is all about overlapping. In RF, we have 2p overlapping, which is stronger bond compared to the of this as 2p and 3, 4, 5. So 5p. Done. Next. Polar protic solvents always favor E1 and SN1 reactions because they want to solvate the molecules and it will helps in breaking the bonds. Water, alcohol, acid, methanol, ethanol, these are all the best examples. It will have a high dielectric constant and it will favor solvolysis. Like water has high solvolysis of 88, ethanol 22, and this is formic acid, which is 50. Okay. Now, RX, which does not favor SN1 reactions, obviously anything which is an unstable carbocation. So you can see methyl carbocation, highly unstable. Vinyl carbocation, highly unstable, as well as partial double bond character is there. So bond breaking is difficult. Phenyl, partial double bond and highly unstable. This is also incorrect. That means it will not go for SN2 reaction. Next. Getting a positive charge here, it will become anti-aromatic. So therefore, anti-aromaticity is one case. Bridged, it violates the Brett's rule, which says that no carbocation can come on, um, no carbocation can form on the bridge head carbons. Okay. RF, if you have an RF bond, it will be difficult to make SN1 reactions. Next, you have this one, C double bond O X. This was the best example for SN2 and this is the worst example for E1, okay, or SN1, because this kind of carbocation is highly unstable. Please go through the order once, everybody. Just go through the order. Upward means it is increasing. You can say triphenyl carbon, it increases, then diphenyl. You can see there are 3 triphenyls here, here diphenyls here. Then if you have any lone pair donating groups, right? Then we have tertiary, then we have phenyl, then we have this is benzyl group, okay, allyl 2 degree, 1 degree, and then we have methyl, uh, vinyl Y. These are all not the reactions which will take place. See the compound and check out rate of SN1. Check it out, everybody. Take some time, check out properly. And everyone. Finished? Sir, in the last two cases, why last case rate is less than that of the last second? Between these two, bridgeheads and this one. Okay, bridgehead is an highly unstable carbocation. I gave you the carbocation order better. Check out the carbocation order. This is less stable compared to that of phenyl carbocation. Okay, and this is more stable compared to that of vinyl carbocation. Okay, clear, Satvik? In table, acha, in table, this is a special case. This is what we call it as SN1 dash. SN1 dash. Okay, because directly attack is not at this position. Attack will be here after removing this group. So that is the uh, SN1 SN1 dash types. Okay, that is what you will observe in this case. That's a special case. Apart of that, check out others. Done? Right. Check out. Since SN1 is going via carbocation formation, it is subject to rearrangements. Because once you get carbocation, it has the ability to rearrange to a more stable carbocation. You will see, for example, if bromine is here, I'm adding it to water. First carbocation will form. Then 1,2 hydride shift will take place. Hydrogen from here will shift, creates a more stable carbocation. And then water will attack. It will convert it to this product. Next, if you notice here, OH is Br is removed. If you treat with aqueous KOH, it might give a bit of SN2. Small composition, not large of SN2, a small composition of SN2. Okay. If it is SN2, via SN2, you'll get only this product. But via SN1, what do we get? Via SN1, first you remove carbocation, positive charge will come. That positive charge will make, methyl shift. That is from here, plus charge is here, this methyl will shift. And when the methyl shift happens, the carbocation will be like this. This with a positive charge here. So once you get that positive charge, water will attack on it. So you will get this as a product with rearrangement. Okay. So you can see in the rearrangement does not take place. If the rearrangement does not take place, then SN1, SN2 mechanism gives the same product. Okay. For example, in this case, this is secondary. In secondary, OH minus, if you attack, you'll get this product only. If you attack water, you'll get this product only. Right? This is major via SN2 type of reaction. This is always major via SN1 type of reaction. Yeah? Notice this case here. If you take OH minus in the presence of DMSO, DMSO is a polar aprotic solvent. In that case, it is highly favorable for SN2. Okay. So then you will get this as OH here without any rearrangement. Okay. But if you have water being added, first you'll get carbocation here. So first we'll get carbocation here. That carbocation will undergo rearrangement because it can get more stable carbocation, which is allyl. Now it is an allyl carbocation. After that, you will get the water being added. So this is the product with rearrangement. Similarly, if you have OH minus in the presence of DMSO, it will go for SN2. So you'll get directly Br is removed, OH has come. But with water, First carbocation will come, it will move here for more stable carbocation, then OH will come. Okay. So in the case of rearrangement, I hope you should know how it works. Next, check out SN1 versus E1. I think I told you this before also, how the SN1 and E1 works. See, E1 has all the features same as that of SN1. There is no change between SN1 and E1 except for the temperature difference. Okay. The conditions of SN1 and SN2 are identical except that at high temperature. Okay. So at high temperature, elimination predominates. For example, ETOH is given, but this time I have mentioned temperature, which means chlorine will leave and ethanol as a base will extract proton from here, or it can extract proton from here. So you will get this or this as a products. And these two products are elimination products. They are relatively major compared to that of this product, which is minor product. Substitution product, which is minor product. Okay. Notice that here, if you have this compound, if you take ETOH and heat, you'll get this as a major product. But without heat, if you identify that ethanol will attack here, Cl will leave. That is via SN2 mechanism. Sorry, SN1. This is SN1 mechanism. Okay. Ammonia attacking here. Now, ammonia is a good base also. Ammonia is a good nucleophile also. Since it is a good nucleophile, it want to go for SN2, but SN2 is not possible at this position. So instead, it will go for elimination. So that means it will take away proton from here. It will give double bond. So that is via E1 elimination. If you take Cn minus, it will give E2 elimination. If you take this phenoxide type of a group, correct, it will go for elimination and it will take H plus from here. It will make this as an elimination and that itself will become enol. Enol will become ketone. C minus will also extract H plus from here, makes an elimination. Okay. So what have you noticed? Even a small concentrated or the concentration of the base is increased or the strength of base is slightly increased. It would usually go for E2 type of mechanism only. So guys, lot of time you will see reactions will either go via E2 mechanism or SN1 mechanism. SN2 and E1 are very less preferable at times. Okay. Clear everyone? Now notice this hydrolysis. This is about the reactions of alkyl halide. Okay. So it is same as SN1. So Cl is been removed, carbocation has come, water has been attacked. So this is what we will get. If it is rearrangement, Br will go, positive charge will come. Rearrangement will happen, positive charge will come here. Now check it out. How many different types of compounds you are getting here? See, first positive charge is here. This is the first positive charge. Second time positive charge is here. And that positive charge can be, because when a positive charge coming here, it could make this methyl group to go in coming out of the plane or inside the plane. So again, I am actually getting two different types of positive charges. So hydrolyze this one and hydrolyze this one. So what are the products you will get? Here, when you hydrolyze it, so from here, for example, let me check out these two. This one, if you hydrolyze it, methyl is outward and OH and Me were, you know, at this position, at a carbocation position. And while if you notice this one, for this OH and Me and OH and Me, if at all I added, so you can see this A and D become enantiomer, B and C will become enantiomer. Basically, you will get two enantiomeric pairs. Okay. Check everybody. Now, if the question is asked about total number of, sorry, that is the next question, right? So for this question, let us just understand major products only. So if you have these products here, this is the product which you are getting as a major product. From there, when you do hydrolysis, these are all the major products. Out of them, you'll notice that A and D are actually enantiomers and B and C are actually enantiomers. Total, we'll get four different compounds. Yeah. Sorry, notice this example. In the example 2, find the total number of products also. I need to find total number of products. For that, first thing I need to do is find all the possible carbocations. See, first carbocation is like this. When bromine is being relieved, this is the first carbocation. Second, by rearrangement, it will go here. This is the second carbocation. So based on that, what are the products I'll get? I will get like this with OH, and this is a chiral center, plus benzene with OH with a chiral center, with a chiral center here. So this is plus or minus, this is plus or minus. So while counting, how many total you will count? Okay, total number of, okay, products, including stereoisomers. So how many we have? Two here and two here. So total four. Okay. Check that out. Do the next one, everybody. Check out how many products you are getting. Basically, it is the same thing which is given up in the question. You just have to apply that once again and try it. Find out everybody, including stereoisomers. You need to check out including stereoisomers. Do that. Done. Let's see what are the products we are getting. So first, we will get the carbocations, right? Let us write all the carbocations possible. This is the first carbocation. After shifting, this is the second carbocation, right? So with respect to first carbocation, if you write the product, we'll get OH. This is a chiral center, so I'll get two products, plus with respect to second one, I'll get OH here. So we have two chiral centers now. With respect to that, I'll get four products. So total how many products? Total six products. Clear everyone? Right. Try the next two. Write all the products possible. Everyone, do the next two. Check the first case. Get carbocation here. The carbocation can undergo further stabilized carbocation. This is what you'll get. So from there, after adding water, we'll get product here with OH. If I add water, I'll get OH here. This is also a chiral center. This is also a chiral center. Here we'll get two products. Here we'll get two products. Next one. There is OH group here. Carbocation first has formed here. Now listen up. This carbocation can go left side also to get more stabilized or right side also to get more stabilized. But you know that right side OH is a more donating group. So it will go more only on the right hand side. Left hand side, not even a small amount will go because rearrangement will always happen on the direction of more stabilizing side. So we can say this side is more stabilizing compared to the left side. So this is what you will have. So based on this, what are the products formed here now? So if you notice the product that will be formed here, okay. So, so the product that will be formed here is OH here and another OH here. So this OH, this is also a chiral center. So you'll get two products. This is also a chiral center. You'll get two products. So again, we'll get total four products here. Check out the fourth one. Everybody notice the fourth one now. Fourth one, we will have first this as the carbocation. From the carbocation, you will see the rearrangement will happen by ring expansion. Ring expansion happened. The positive charges come here. Okay. If you check out with the numbering 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, 6. So between 1 and 6, there is a bond formation. This is the carbocation which is formed here. So from this carbocation, again, I can say we can have one more rearrangement which will happen to go here. So from here, if you directly add water, I will get product as this one, OH. And that is a chiral center, which means I'll get two products from here. Here, if you notice, I have here and OH, correct? Here, this is also chiral center. This is also chiral center. So you get how many products? Four products. And here, when you add water, you'll get OH here. This is not a chiral center, so only one product I'll get. So total number of products. So total 7 products you'll get. Everybody check these two cases. Yeah. Next one. Check out next one. Here. We need to remove this chlorine. Put this O group here. So first carbocation which will be formed here is this will be the same, but here we have CH3 carbocation. This is the first carbocation, and here it is H and CH3. Okay, the chiral center will remain, and from here you will get one more carbocation here. Right. Next, now we notice this carbocation will be rearranging to this one CH3. Okay, sorry. So here we'll have CH3 carbocation, and next we have CH2 CH3. This is what you will have. Okay. Now from here, if you get the carbocation product here, we will get this as CH, CH3 and OH. H and CH3. See, notice this one. This chiral center is fixed. Now we got a new chiral center. Okay. So if the number of compounds with respect to this, if you notice, this chiral center will have only two products. So that means you will get only two products from here. Okay. Next, with respect to this, when you add water, now we will get C, CH3, then ET, then OH. So this is a new chiral center that will make two products. So total 4 products in here. Okay, not 6, it should be only 4. Check that. Okay. Now these two which are there, these are pair of diastereomers. Pair of diastereomers. While these two which are there, these are pair of enantiomers. Done? Done? Everyone got that? See the next question. With ETOH, first we'll make a carbocation here, and that carbocation can undergo further rearrangement to this place because that is more stable carbocation position. Okay. So from here, if you add ETOH, we'll get this as OET. So it is a chiral center form. So two products I'll get. With respect to ETOH here, OET, this will be the chiral center, two products form. Okay. Guys, listen. After the rearrangement, the last carbocation on which you are adding, that is always the major product because that is a more stable product. Okay. Done with this question, right? I told you about racemization already, that once you get a carbocation, water could attack or nucleophile can attack from either of the directions. Okay. So we'll get this product and this product. And like we discussed earlier, inversion will be slightly more than that of retention. Okay. Why? Because due to tight ion pair, always there will be small amount of inversion amount, slightly more than that of retention. Okay. So percentage of racemization is always proportional to stability of carbocation. More stable carbocation, racemization percentage will increase and pure form will only be 2%. Correct? Right. Now check out. When does SN1 reaction takes place? Okay. So first case, check out. Rx in the presence of all of these cases. Definitely SN1. This is definitely SN1. Rx in the presence of Lewis acid, right? Where we have, something like Ag plus is trying to get a precipitate formation. In case of precipitate formation, then also we'll get this. Okay. So here, sorry, this is not OH, this is Cl. This is X. X could be chlorine, bromine, or iodine. So in the presence of moist Ag2O, it will go for SN1. That means moist Ag2O. See, let me tell you what is this moist Ag2O means. When you have moist Ag2O, moist Ag2O is, it is 2Ag plus O2 minus. Okay. And the minute you have moist Ag2O, that means when you add water, it will convert into 2 moles of OH minus. Okay. So basically, moist Ag2O is same as saying that I have an Ag plus ion and OH minus ion. So remember that moist Ag2O is same as saying that it has Ag plus ion and two OH minus ions. Okay. Right. So check it out. So therefore, if you have moist Ag2O, then if it is Br, if there is Br here, let me write down Br here. Then the precipitate formed is AgBr. This will become a carbocation. Water will get added and you'll get this alcohol. But if you're direct nucleophile like OH minus, F minus, Na minus, SH minus, then it will go via SN2 mechanism. Direct attack will happen and you'll get this as the product. Got it? So this is first case where you can, second case where you can get carbocation formation in the presence of moist Ag or Ag2O. Okay. So quickly go through the differences between SN1 and SN2, everybody. Just read it out. What is SN1? What is SN2? I hope all of you read that.
So 1 minute.
Hmm. Yeah. Right. See, typically, when it comes to rate here, okay, with water, for example, when you treat with water, this is how the SN2 would happen because this CH3Br rate, if you notice, more SN2 will be favorable, correct? As you come towards primary, slowly it will start decreasing. And by the time it comes to secondary, both SN2, SN1 are favorable. And by the time it comes to tertiary, only SN1 is favorable. Okay. So this side mostly it is SN1 kind. This side it is mostly SN2 kind. Okay. Try this, everybody. First question. What is the product? It is SN1. So definitely we will have OH here. Okay. And you need to understand that when it comes to this group here, methyl is like this. Methyl is this way, but here Cl can be this way also, and Cl can go inside also. Why? Because it is at a carbocation. So this will be 50%. Sorry, not 50%. This is not a chiral center. These are the two products you will get, and these are geometrical isomers. Second case, OH. OH minus, you'll get only one product, inversion product, only one product, because this will go via SN2. Next, check out in first case. If you take this position Br with water only, SN1 will happen. So SN1 will happen. So it can give OH here, methyl here, like this with a chiral center, and plus and minus both will form. Plus and minus both will form. Here we have 20% DMSO, 80% water, correct? Still, what I would suggest here is you need to get this thing clear that it will be 50-50%. While in the second case, if you notice, water, as long as it is 80% present, that means still it is going to have OH here with almost 50-50%. Okay. And if it is only SN2, So then OH will be here. This will be 100%. Okay, so this will be 50-50%. Here also it is 50-50%. While in this case, you'll see that. Now, tell me, my question here is about first and second product here. First reaction and second reaction. Now, in the first reaction and second reaction, where do you think the racemization is more? Everybody, think about it. Where do you think the racemization will be more? Notice this one. In the case of first case, what is happening? Since there is only water, 100% there is only water, it would always have some part of inversion, because we have noticed that immediately inversion can take place because you have large amount of water present. So I can say here, okay, between 1 and 2, between 1 and 2, okay, 1 will have less amount of racemization, less amount of racemization than 2. Got it? So when you have a mixture of some amount of DMSO and water, then the percentage racemization will always increase. So keep this in mind. Okay. When you have some amount of aprotic solvent added, then the percentage will increase, because now water quantity, right? Water quantity, whatever we have here, right, is not very high that inversion will immediately start. Correct? So slowly it might take some time. So by the time you already have the ions separated. Got it? Done? Right. See the next question. Here we have formic acid. So again, bromine is being removed. So we'll get this as ester OC double bond OH plus Br minus. So this is a chiral center. We'll get two products here via SN1. Here also we have double bond Cl. See, when you have allylic position, right? This is where there is an allyl here. Sorry, allylic position. This is where the isotopic carbon. Now this carbon, let us say we call it as an isotopic carbon. Isotopic carbon. If it is an isotopic carbon, I know that the carbocation which is formed here will undergo resonance stabilization to get carbocation here. And the chances of both are 50-50 percentage. So this is also 50 percentage. This is also 50 percentage. So that means the product what you will get here is OET. This is 50 percentage chances, and double bond with OET, with this as a chiral center, sorry, with this as a isotopic carbon, this will also be 50%. Okay. So when you have same allyl group, that means the resonating structure is also same in allylic position. In that case, we can say 50-50 percentage will be formed, right? If you have the notes, make a note of it. Finished? Right. Next one. This we discussed. This is an SN2 dash where you have an at allyl position. This is where it will connect. right? Br will go from here. So the reaction would happen like this. PH S minus, it will connect from this end. Br will leave and double bond will shift here. So we will get this as PHS connected to CH2 with CH double bond CH2, and this is where we have the center. So this is major product which you will get. Okay, direct attack on this carbon is less favorable in SN2. Rather, it will attack from the other end. Why? Simple reason. You see, this one is sp3 hybridized and this one is sp2 hybridized. Always preference will be more on sp2 hybridized because that is less crowded. So since it is less crowded, you will see attack would happen more on this end compared to that of sp3 carbon. When it comes to ETOH here, in case of ETOH, first we'll do a carbocation formation. First we'll get carbocation here. Then carbocation will undergo rearrangement here. So we'll get double bond and positive charge here. Okay. So now you can see the more stable carbocation is this one. So both will form reasonable in reasonable amount here. So we will have OET also here and we will get double bond OET also here. Correct? Both will form in a reasonable amount because both are resonance stabilized. Resonance stabilized means both will have reasonable amount, but slightly more stable is this one. This one is major, this one is minor. Correct? So I can say that this product is via SN1. This product is, sorry. This is via SN1 both case, right? Minor. Done, everybody? So I hope you got an idea about SN1 and SN2 reactions, how to deal with it. I suggest all of you to finish up the assignment which has been given to you. Everything related to SN1, SN2, E1, E2 should be completed by tomorrow. Okay. If you can't complete, see, I'm noticing your marks, correct? Lot of silly mistakes are happening.